did it. We solved the triangle. We solved it carefully. We used the equations. We used law of cosines. We paid attention to which application of the law of cosines was better, depending on which corner we stand. Every time you stand at a corner, you got involved 4 variables. You count which of the 4 variables are known, so that you only have one unknown. Okay? Very, very nice. This is a standard example. Let's run by that one more time. Another example before we get into some more slightly demanding examples. Okay, let's try this one. Suppose you stand on this corner over here. Let's label all of the ones we don't know. Let's call this one A, B, little b. Those are the 3 we don't know. In fact, let's make them a different color, just for fun. Let's say they are blue. So I'll call this A, capital B, little b. Okay, those are the 3 pieces that we don't know, and these are the 3 pieces that we do know. If we stand on this corner over here, think about it. From this corner, which sides would be involved in the application of law of cosines? These 2 would be involved, and those 2 would be involved. Out of these 4, how many are known and how many are unknown? You have 2 unknowns and 2 unknowns. Not a good thing. Okay, if you stand on this corner over here, which quantities would be involved? These 2 would be involved, and these 2 would be involved. These 2 are known, but these 2 are not. You'd have 2 variables in that equation that you don't know. That's not a good thing. If you stand on this corner, whoa. If you stand on this corner, how many unknown variables do you have? These 2 are known, and this one is known. You will only have 1 variable, so this would be the optimal application of the law of cosines. We should take our little guy here. Let's just make a new one over here, and apply the law of cosines from this point of view. From this point of view, it'll look like this. 10 squared is equal to 3 squared plus b squared. Now, if it was just the Pythagorean theorem, you'd be done there, but this may not be a right triangle, so you'd have to compensate by doing this. Minus 2 times 3 times b times a cosine of 40 degrees. That's the law of cosines from this point of view. Count the number of variables. 1. I told you. It's perfect. And now we could play this game. 100 is equal to 9 plus b squared minus 6b times cosine of 40 degrees. Say, what kind of equation is this? You've got a b squared, got a b there, got a constant there, constant term there. It looks like a quadratic equation. If you recall, the way we solve quadratic equations, move everything to one side. One way to solve them, anyways. This would be, let me think, this would be negative 91. So this would be b squared minus 6 times cosine 40 degrees times b minus a 91. When you see this, you should be thinking about an equation that has degree 2 equation in standard form. Let me remind you. This looks like this. Let's go off on the side here. A little side job. Ax squared plus bx plus c is equal to 0. If you have such an equation, then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. You remember that? It's quadratic formula. Super famous. That's exactly what we're going to use to solve this one. Our x is the b. Coefficients are 1. This guy right here, 91. Maybe I can simplify that one just for fun. 6 times cosine of 40 degrees. What is 6 times cosine 40 degrees? Let me bring my magic number machine. I want to do 6. Can you see it? There. 6 times cosine of 40 degrees. That is approximately 4.6. So this is 0 is equal to 0 is equal to b squared minus 4.6 times b minus 91. So therefore, b is equal to negative b, which would be 4.6, plus or minus the square root of b squared That would be 4.6 square, negative actually, minus 4 times A times C all over 2 times 2 times A. Is that right? You remember doing this in high school, don't you? Junior high, elementary school. Alright, so this becomes B. B is equal to 4.6 plus or minus the square root all over 2. I gotta simplify that, guys. 4.6 square minus 4 times negative 81. Let's see if we can do it. That guy squared is equal to that plus 4 times 91. I'm doing plus because this is minus minus. That will give me 385 point whatever. Then I'll take the square root. So I'll take the square root 0.5. That would be about 19.6. Okay. So this is about 385. And that becomes B is equal to 4.6 plus or minus about 19.6 all over 2. So B is equal to, if you take the plus, let me think, if you take the plus, you'll do that. Plus 4.6 is equal to that, divided by 2 is equal to that, about 12.11. Or B is equal to, let's do the minus, so it'll be 4.6 minus 19.6 is equal to whatever divided by 2, that's equal to 7.5, negative 7.5. So B is 12.11 or negative 0.75. Now for now, if we assume that our lengths are positive, then only one of these will work. The B this is B is negative, that one's positive, so B must be approximately 12.11. See that? Told you. And the other one wouldn't be a Euclidean triangle. It might still be a solution, mind you, but in some other land, La La Land. Not really La La Land. I should be more respectful in non-real land, which is actually a beautiful place, but that's slightly beyond our course. So anyways, this is a real solution, 12.11, and that takes care of B. And then you could solve for some of the other ones. Let's solve for the angle B. You want to? Let's do it. So let's actually solve for A here. I'm going to do some analysis here to make sure that it's going to work out. If I involve these two and those two quantities, total of 4 quantities, which of them do I know? I know this one and I don't know that one, so that's one on, but I know these two, so a total will only have one variable in that statement of the law of cosines. So this will work out here. Let's do it. So I'll apply it from here. From here it looks like this. It'll say 3 squared is equal to 10 squared plus 12.11 squared. Right? That's the beginning of the Pythagorean theorem. And if it was Pythagorean theorem, we'd stop there, but it's not. It's a law of cosines, so we subtract 2 times 10 times 12.11. So 12 times a cosine of A. Right? And then we just clean it up. 9 is equal to 100 plus whatever that is. Let me bring out my number machine here. 12.11 12.11 squared. How much is that quickly? I was going to say that 146.65. 146.65 approximately, minus 20 times 12.11. 20 times 12.11, that's equal to 242.2. 242.2 times cosine A. Clear? That becomes 9 is equal to 246.65 minus 242.2 times cosine of A. In case you're wondering, I put these two together. I added these two. Added them, that gives me my 246. Next, I'm going to move the 246 over to the other side. So I have to take 9 minus that, 246.5. So I go 9 minus 246.65. What is that equal to? Negative 237.65. So this will be negative. I'm getting old, man. I can't even remember. Negative 237.65. 237.65, and that's equal to negative 242.2 cosine A. Now what we want to do is divide both sides by this quantity, divide this by negative 242.2, divide that by negative 242.2, so that we can isolate and figure out what cosine A is. Cosine A would be negative 237.65 divided by negative 242.2. And once again, we'll use our little magic calculator to approximate that. Many of these should have approximations. Again, sometimes I forget. What will that give you? Let's see, 237.65 divided by 242.2. Of course, it's negative. So that will give you a total of 0.9812. 0.9812. Again, this is a standard equation. We solved it correctly and honestly by graphing it. Let me think. The graph goes something like this. The graph of cosine goes like this. There are infinite many solutions. 0.98, somewhere around here. 0.98. You got solutions all over the place. You got solutions here, solutions there, solutions there, solutions there, solutions on the left side. But keep in mind, we're looking for a solution that's an angle inside in the interior of a triangle, of a Euclidean triangle in flat land and real land. So this angle's got to be, of course, it's got to be between 0 and 180, because that's the sum of the entire sum of these three angles. So this one's not going to work for me because it's close to 360. It's more than 270 for sure. This is a 270 mark, and this is past it. In fact, by analyzing all the solutions here, I can see that the only one that's going to work for this problem would be exactly this one, which we can get by doing a little cosine inverse. And again, you may think, well, that's kind of silly. Won't it always happen that way? And the answer is no, definitely not. Sometimes some of these angles will actually work, and you'll get two possible triangles. Okay? And it's not really a big deal. You don't have to remember when will I get two triangles or when will I... You just have to solve the equations correctly and honestly, and they will tell you when you have two triangles, or when you... The other possibilities are you may have 0 triangles, none, no real triangles. Other possibility, you may have infinite many. In fact, that's it. You either have no triangles, no real triangle solutions, exactly one real triangle solution, exactly 2, or exactly infinite many. There will never be exactly 5 triangle solutions. No. 0, 1, 2, or infinite. That's it. Okay, where was I? We got to figure out this angle. The first one is, let's do a little cosine inverse. So I'll do shift. First of all, let's clean that up. Shift cosine of 0.9812. That is, make sure you're in degrees, 11.12. So this angle right here, 11.12 degrees. The other one is that short of 360, so it's about 350, 349. Of course, we can discard it, so I can conclude that A is approximately 11.12 degrees. Okay? And for this one, we just subtracted from 180, so I'll go 180, take away my 11.12, take away my 40 that I had before, 128.88. B is approximately 128.88 degrees. There you go, we solved it. Now you see why they pay me? Insane amounts of money? You thought these were just a pair of pretty hands, huh? Alright. This is perfect example, standard, routine law of cosines to save the day. Okay, law of cosines. You know, the brand new shoe compared to the old Pythagoras theorem. This one will solve all of the triangles, all of the ones in flatland, and all the real triangles. Alright, so maybe we're pretty much done, except that we should talk about the possibilities. Okay, I mentioned before that sometimes you may get more than one triangle. Sometimes you may not get any. It's just, you know, anything could happen. When 3 items are given and you got to find the other 3, these are the possibilities. You may have 0, no real triangle solutions. You may have exactly 1 real triangle solution. You may have exactly 2 real triangle solutions, or you may have exactly infinite many real triangle solutions. This is it. These are the only possibilities for triangles. We've already done a couple examples of that. Of this one. These are the examples we've done where you have exactly 1 real triangle solution. Perhaps it might be good to do one of the other ones or a couple of the other ones to see how they work out. You don't have to remember anything. You don't have to do anything special. You just solve the equations correctly and honestly, the way we practice. Okay, let's try some of the other ones. Here's one way to think about it. Suppose you have a whole bunch of possible lengths of the sides. These could be the sides of a triangle, and we could throw them in a bag and just pour them down there. And besides sides, you also have angles. Suppose these could be the angles, like this is a small little tiny angle, and this is a much bigger angle. And suppose you throw those in the bag. The idea is that if you pick any three of them, could you solve the triangle? The possibilities are these. Maybe there is no real solution. Maybe there's 1, 2, or infinite many. That's it. So let's pick out. Suppose I pick out. I reach in the bag and I pick out, say, 3 sides, for example. 3 sides. These 3 sides. The idea is, can you make a triangle out of it? And if you can you make more than one? And if so, what are the rest of the measurements? And so, let's just say this one, for example. I have a one of the sides which measures, say it measures 6 inches, and the other side measures 2.5 and 2.5 and 2 3/4. So let's just say one of the sides is 6, the other one is 2.5, and the other one is 2 3/4. This is the sides. Now the truth is that you really can't. Well, how could we make the triangle out of this? You can't really put them this way. Say maybe it's supposed to go this way. And you can't do it that way either, because this one seems to be too big. In fact, no matter how you try, these sides are not compatible. And so this would be one of the cases where you have exactly zero real solutions. And you don't have to remember or try to think about really hard about, hey, when will it be the case that there's no solutions? If you can't see it right from the top, I'm telling you, you can always trust the equations. For example, suppose you just ignore that and you went ahead and say and you try to solve for it. Here's what would happen. The equations would not lead you down. They would tell you, hey, that's impossible. You're kidding yourself. If this side is 6 and this is 2.5 and this is 2.75, you say to yourself, all right, I'm going to go about my happy self and solve for it. I'm going to use the world famous law of cosines. I can do that because if I stand from this corner, at least 4 will be involved, and I only have one variable, the a, so it'll be no problem. And so you go on and you say to yourself, all right, 2.75 squared is equal to 6 squared plus 2.5 squared. Minus 2 times 6 times 2.5 times cosine of a. And you say to yourself, hey, that's a nice equation. All we have is one variable, a. And so you clean it up and you get that. I'm just going to skip a lot of the grunt work here. Cosine a is equal to. So I use my my little magical number machine here to compute it, and I get that cosine of a is equal to 1.15. And then again, I do it the usual way. I draw my cosine graph. Here it is. And I draw the other graph, which would be 1.5, and I say to myself, where do they intersect? They don't intersect in the real plane. There is no real solution to this. No real solution. So the nice thing about this is I'm telling you the equations could never let you down. If your common sense fails you, look, this is 2.5, this is 2 and 3/4. There's no way you can make a triangle if this one is 6. That's common sense, but if it fails you, the equations will never fail you. They'll tell you there's no real solutions, or there's exactly one real solution, or there's exactly 2 real solutions, whatever the case may be. So that takes care of an example where you have exactly 0 real solutions. That would be that one. Let's take a look at one where you have infinite many. Suppose I throw these back in the bag, and suppose this time I choose one angle. Whoa. One angle that moves, and I'll choose another angle, and I'll choose another angle. And here are the 3 things that I've chosen. The 3 angles, and suppose these angles happen to be, I don't know, I'll measure this one, say it's, I'm just going to estimate here. Suppose this angle is, I don't know, let me think. Suppose this one is 20 degrees, suppose this one is 60 degrees, and suppose this one over here is 100 degrees. Well, maybe I'll be a little bit more accurate. This is 20 degrees, 60 or 100 degrees, and 60 degrees. Great, they add up to 180, so this is a possibility. If they didn't add up to 180, you say it wouldn't be a real triangle, there's no solution. If you just get lucky and they add up to 180, well, then you got none of the sides, so you really don't know how big it's or small it could be. It could be huge, as large as the universe, or it could be small, smaller than the pin, than the tip of a pin. So this one would have infinite many solutions. Infinite many solutions. Again, you don't have to take my word for it. The equations would never fail you. You could apply the law of cosines here, and you'd see that there are 2 unknowns. And if you know a little bit about systems of equations, you do that on every corner, and you realize that there are infinite many solutions to that system. Okay. So that would be the case where you have exactly infinite many solutions. The only one that's left to do is the one where you have exactly 2 solutions. It's probably instructive for us to finish this with just one example, at least one example, where you have exactly 2 real solutions. So let's see it. So suppose this is the case. You have 20 here, 6 there, 10 there. 3 items are known and 3 are missing. So let's label the ones that are missing. And let's call this one big A. That means that one across from it is little a. Let's call this one big B, across from it little b. And so you go on and we could apply the law of cosines. For example, let's apply it here, since applying it here from this point of view would involve these quantities, and these are known and one of these is known, so that would leave you just one variable, which is really nice. That's exactly what we want. That will help us solve for B. So we go on and we go like this. We go from this point of view, 6 squared is equal to 10 squared plus b squared minus 2 times 10 times b times cosine of 20 degrees. Okay, then we clean that up. That gives you 36 is equal to 100 plus b squared minus 20 times cosine b times b. That gives you 0 is 100 plus, actually, 20 cosine b times b. I'm going to clean this up, set everything equal to 0, and that gives me b squared minus 20 times cosine, well, this was 20 degrees. Let me go ahead and compute that. 20 times cosine 20 degrees. What is that? 20 times cosine of 20 degrees. It's approximately 18.8. So this is 18.8b plus 64. If you're wondering where I got the 64 from, I subtracted that from 100 and then moved it over to the other side. Okay, so I got my b squared I came from here, then there. I got my linear term. This is the degree 2 term. Degree 1 term, 2 times sin is 20 times cosine 20. That would be this one, which turned out to be 18.8. And 64 from the 100 minus 36. So that's a quadratic equation. That tells you the solution. The solution, we can apply quadratic formula that gives you that b is equal to 18.8 plus or minus the square root of b squared, which is 18.8 squared, actually negative squared, minus 4 times a times c, all that over 2 times 1. And that, after it's simplified, you get b is equal to... Okay, so I skipped through all the grunt work here. We plug this, we solve this quadratic equation. You get the 18.8 plus or minus square root of 68 divided by 2, which gives you two possibilities for b. b is approximately 5.25, or b is approximately 13.25. And you say, what happened here? Well, think about what was given. You were given this side, which is 10, and you were not given anything about b, and you were given side 6 and 20. If this is all you're given, this one really has a freedom to be, because there's nothing known about the angle b. This could be here, or it could be there. If it's there, maybe the b is approximately 5 point whatever it was. But maybe if the b is here, the b is approximately 13 point whatever it was. So that's why you're getting two possibilities, because you could have that being there, or this be the 6 being here. That way you have either a little b, which is approximately 5, or a larger b, where b is approximately 13. And so this, at that point, you say to yourself, okay, if I have to solve this triangle, I have to break it down to two possible cases. First case, where b is the larger one, I'm going to go with b is equal to 13.52. So in this case, b is equal to 13.52, and I'll solve this one. But the other case is where the drawing actually looks more like this, and forget about that one. That one's got to be moved over here. And this one, forget about this one. This one's much shorter, and my b is approximately, in that case, 5.25. This is approximately 5.25. So now I've got two cases to deal with: the one with the large b, and the one with the small b. Of course, finishing this is easy, because now you can apply the law of cosines from anywhere. For example, you can apply it here. If you count how many unknowns you've got there, you've only got one unknown, the a. So you can figure out what the a is. You'll just go like this. You'll go like this. From this point of view, you'll go 10 squared is equal to 6 squared plus 13.52 squared minus 2 times 6 times 13.52. I know you're running out of room. Times the cosine of a, times the cosine of a. And then you clean it up and you'll get your a. A is approximately whatever. At that point I don't even care. I'm not going to finish that. I'll let you finish that. And similarly here, you would apply the law of cosines from this point of view, because that would involve these variables, these ones and these ones, of which you know all of them except the a, and you would solve for it. And this would be an excellent example where you have exactly two solutions. There's nothing to remember. All you do is solve the equations correctly, and you're good to go. Okay, that should get you guys going on the homework. This is a milestone for our class. With this, we conclude what's commonly known as basic trig. Solve triangles, right triangles and non-right triangles. We'll come back and do a little bit more of this next time with the law of sines, but this is actually the heart of it. Okay, the law of sines will be a small, little tiny lecture. This is a huge one. We did the law of cosines, the trick stuff, the situation, we needed to solve them, the medicine, give it some law of cosines. Of course, that should get us ready that's about it.